In our last video, we looked at quadratic equations and how to find the vertex and determine if the graph opens up or opens down, so that we can kind of quickly take a quadratic and graph it and see everything we care about when we look at an application. Now we're going to kind of expand on that, and we're going to look at a whole class of functions called polynomials. As far as mathematical definition goes, there is a mathematical way to write polynomials. We say p of x equals a sub n, x sub n plus a sub n minus 1, x to the n minus 1, all the way down to a sub 2 x squared plus a sub 1x plus a sub 0. And that's kind of a big, long, convoluted algebraic way of writing something that we like doing in math. For the purposes of this, all we really care about is the understanding of what a polynomial is, and essentially most of what you have worked with in all the math you've ever done has been a polynomial, because polynomials are nice and neat. So if I have something like p of x equals 3x squared plus 6x minus 2, in order to be a polynomial, I need a variable. Call it x, call it whatever you want. I have a variable here. That x has to be raised to integer powers, and more to the point, to non-negative integer powers, meaning no negative numbers. So in this case, x is squared, x is raised to the first. Technically, we can say that's x to the 0. So all of my powers for my variables are nice and neat, no negatives, no fractions, no nothing like that. And all these a's, this a sub n, a sub n minus 1, and all of that, those are just numbers, coefficients, constants. 3, 6, 2, stuff like that. And they can be anything. So basically, that quadratic that we're used to working with, that's a polynomial. We looked at lines. If I have something like f of x equals 2x plus 4, there's a variable raised to a nice, neat power. I have coefficients, constants. I'm good, that's a polynomial. Even if I have something like this, p of x equals 4. There's no variable there that we see, but technically there is an x to the 0 here. That's called a constant. I mean, we know it's a constant, but it's called the constant polynomial because we don't write to the x to the 0, so we just write the 4, but we understand there actually is an x there. So again, all of these things we've seen and worked with are polynomials. But we can just as easily have something like p of x equals 3 x to the 5th plus 4x cubed plus 7x squared minus 9x minus 4. Now I have an x, but it's raised to a whole bunch of powers, 5, 3, 2, 1, 0. Those are all nice non-negative integers. And I have a bunch of coefficients, constants, so I'm good. That's a polynomial. If we have something like this, p of x equals 3x squared plus 2x plus 4 plus x to the negative plus 3x to the negative 2. In this case, this x to the negative 2 power, that's like really messy. If we remember our rules of exponents, negative exponents flip, so that's really 3 over x squared. That's really messy and hard to work with, so that's not a polynomial. It doesn't have neat powers, so that's not a polynomial, and essentially we won't be looking at them. If I have something like this, p of x equals 2x squared plus the square root of x. In this case, this square root of x is really messy. If you remember your rules for radicals, that's really x to the 1/2 power. That's not a non-negative integer. 1/2 is a fraction, not an integer. That's not neat, so this isn't neat, so that's not a polynomial. And we're not going to worry about that. All we really care about are things that are nice and neat. Easy to work with, easy to graph, easy to find all the information we care about. But before we actually get into working with these, there are some properties of polynomials that are important, understanding the definition. One thing that we will be using a lot is the degree of a polynomial. The degree of a polynomial is essentially the highest power of x, assuming it's a single variable polynomial, the highest power of x in your polynomial. And all you really have to do is look at it term by term. Here, I'll get rid of this so we can see it all a little clearer. Here, highest power of x, different color so I can see, is 2. So this polynomial has degree equal to 2. Highest power of x right here is 1. That's linear, we don't draw the 1. So that means the degree equals 1. Here there's no x, but we said there's really an x to the 0 there. This has degree equal to 0. For this one, we look at all the x's. The highest power of x is right here. That's degree equal to 5. Generally speaking, when we write our polynomials, we write them in what's called descending order. That's how this definition is written, from the nth power, the highest power, all the way down to the 0th power. So a lot of times, if you're looking for the degree of your polynomial, if it's written in standard form, you just look at the first value of x, whatever its power is, that's the degree. But keep in mind, you could just as easily say p of x equals 3x squared plus 6x cubed minus 9x plus 8x to the 12th. That's not written in standard form, but if you want to find the degree, 2, 3, 1, 12. 12 is the highest, that's the degree right there. Okay, so this is not really a very tricky concept to think about. So we need to know the definition of our polynomials, and we need to be able to find their degrees. From there, what we want to do is what we've been doing with all the other functions we've looked at. Graph it. Ultimately, throughout this entire chapter, we're going to look at different tricks to graph polynomials and other types of functions. But we don't know most of those tricks yet. So right now, we're just going to kind of start with easy polynomials. So suppose I have something like this. P of x equals x minus 2 squared, x plus 4, x plus 4, try to make this as easy as possible, x minus 5 squared, x plus 7. First off, is that a polynomial? Well, it's written in factor form, but we know if I FOILed all of this out, I'm not going to, but if we FOILed all of that out, I would end up getting a big, long expression. I'd have a bunch of x's. They'd all be raised to integer powers. So it will be a polynomial, but I'm going to need to know the degree. And as far as finding the degree goes, if it's in factor form, all you do is add up the powers of all the factors. We understand this is 1 if it's not listed. So I get 2 plus 1 plus 2 plus 1. That's 6. So this polynomial has degree 6. When I then want to graph that polynomial, there's really 2 things I care about. 1, the behavior around the zeros, and 2, the end behavior. So when graphing it, we're going to look for this, we're going to look for that, and then basically we're just going to play connect the dots and literally just connect a bunch of dots together. To start with the behavior around the zeros, the way you graph this, first you plot your zeros. Like I said, for a regular polynomial you have to do a lot of algebra to find zeros. We'll learn that later in this chapter. For right now, I gave you the zeros. It's in factored form. The zeros will be at 2, negative 4, 5, and negative 7. I'm going to extend my graph a little bit. And now, I need to find the behavior around the zeros. And for the behavior around the zeros, there's this rule that says if the degree is even at the 0, you bounce off the axis. If the degree is odd, you cut through the axis. Meaning, well, at x equals to 2, which is this 0 right here, that's even degree. So I'm going to bounce off the axis. If my function is coming down, I hit the 0 there, even degree will make me bounce off and do that. Or if I start below the axis, I'll come up, hit that, and then bounce off. At say x plus 4, which is -4 right here, that's odd degree, which means I cut through the axis. I either go from positive to negative, or from negative to positive. The only problem is, I don't really know which way this looks. I don't know if I should be going negative to positive, positive to negative, or if this should look like that, or like that. One thing I could do is to simply plug in a bunch of points, get an idea of where the graph is positive and negative, and then I'd understand better how to graph it. But for the purposes of this, we're going to do something else. We're going to look at the end behavior of the graph. And as it turns out, if you look at, say, that graph right there, or better yet, we'll look at a separate function. Suppose I have x to the 6th, 6th degree, just like this, plus 4x to the 5th, plus 9x cubed, plus 11x plus 7, something like that. Well, I want to kind of figure out the end behavior of what the graph of this would look like. The end behavior is pretty much what the graph is doing as I go way over there or way over there. Well, as I go way over here, x gets really, really big. And if you think about it, well, as x gets really big, say x is 10. I know that's not really big, but if x is 10, that's a 10. 10 cubed is 1,000. 10 to the 5th is 100,000. And 10 to the 6th is 1,000,000. Now on that entire graph, what part of that function kind of dictates the value of the function the most? The x cubed, the x to the 5th, or the x to the 6th? Well, clearly, this is 10, that's 1,000, 100,000, 1,000,000. This term kind of dominates the overall value of the function. These don't change it much. Well, what if I went further along? What if I looked at x equal to 100? When x is 100, if that's 100, now I have to try to do math in my head. 100 cubed is 1 followed by 6 zeros. So that's 1,000,000. 100 to the 5th is 1 followed by 10 zeros. I'm not even going to write that out. 100 to the 6th is 1 followed by 12 zeros. And again, the point is, no matter how big these terms get, this thing, as x gets bigger, the first power right here is going to dominate the overall value of the function. Which means, to a certain extent, if I want to know how to look at the end behavior of that whole polynomial, I really just need to know the end behavior of that function right there. That's actually called the power function, and there are some tricks to figure out how to graph a power function and what it does, but I'm assuming you people like to watch movies and things like that. And you know, nowadays, a lot of movies have like multiple parts to them. Right at the end, something really, really incredible happens. And then they say to be continued, and the credits roll, and you have to wait another year to see the next part of the movie, to see the conclusion. And that's what we're going to do here, because this video is kind of long. I'm going to make another video, and we'll come back to this, figure out the end behavior of that thing right there, and then maybe actually graph that polynomial.